All right, welcome back. So now we're going to go ahead and talk about a little bit further in depth of conservative versus non-conservative forces. Okay, so conservative forces is going to be work done by or against um, the object, depends only on the starting and ending points of motion and not the path taken. Okay, so what does this mean? This means if I have 2 points, A and B, okay, if I choose the straight path here, in a conservative force, my work being done is going to be the same as if I chose a different path, W2, okay? So my conservative force, my work in the first path is the same as the work done in the second path, okay? So it doesn't matter what path we take, okay? On the other hand, non-conservative forces, okay, they do depend on that path that's taken. So again, I have 2 points, A and B, and I first travel, and I have some work done here, W1 versus W2. My non-conservative forces says that these two amounts of work are not the same, even though they go from A to B the same exact way, okay? Just a different path. So in order to take that into consideration, we're gonna have to treat them a bit differently, okay? So now instead of our net force just being the work done by conservative forces, we are also gonna have to take into account our non-conservative forces, okay? And that's where we get this equation here. So our net work is still equal to our change in kinetic energy, okay? But it's also going to be equal to our conservative work and our non-conservative work, okay? Now our non-conservative work also has potential energy and kinetic energy involved with it, okay? So now it's not going to be equal to 0. The change in kinetic energy plus the change in potential energy is non-zero. Okay, so non-zero. I don't know why I put an equal sign there, but it's just non-zero. Okay. As you saw in the last one here, conservative forces, this change is 0. Okay. And that's where we got this value here. But when we're taking into account our non-conservative forces, we have to say that that's non-zero now. Okay, so we get this new formula or equation here. Whoops. Let's go ahead and erase it. We get this final equation here, okay, and that describes our motion now, our work and our energy, okay. An example of non-conservative forces are friction, okay, and that's because with friction it creates thermal energy that's dissipated and it removes energy from the system, okay. So let's go ahead and look at an example of this, okay. So here's our example. We've got a baseball player with some mass equals 65 kilograms, and he's running uphill with a degree of 5 degrees at a 5-degree angle, okay, upward. The player starts sliding with a velocity of 6 meters per second. And there is some kind of frictional force involved, which is 450 newtons. And we want to know how far he slides, okay? So we want to know what this displacement is here, okay? So we want to start with our equation that we just found with our non-conservative forces, our initial potential energy, kinetic energy, plus our potential yeah, our potential initial energy, or initial potential energy, there we go. Getting the words kind of mixed up. Plus our work by our non-conservative force equals our final kinetic energy plus our final potential energy. Okay, so now let's go ahead and think about this for a second. Okay, so we are given that he has some kind of initial velocity, so we will have our kinetic energy involved. So we have 1/2 mv0 squared. Okay, our starting potential energy is going to be, remember that it's based on height here, since we're just looking at gravitational potential energy, but our initial height is just 0. So remember that gravitational potential energy is mgh. So our h here is 0, so we don't have an initial potential energy. Okay. Now our non-conservative work being done is based on our force. Okay. So that is going to be F times D times cosine of theta. Okay. I'm going to put theta prime because it's not based on that theta. Okay. So then that is going to be equal to our final velocity. Okay, and we are looking at how far he slides. So at the end here, it would be when our velocity is 0. Right? So if our velocity is 0, then our kinetic energy is 0. Okay. Now our potential, our final potential energy is going to be non-zero since he gained some height, since he's at an incline. Okay, so it's going to be our mass times our gravitational acceleration times some height. Now our height, it does already give it to you, but it's easy to figure out with trig. Okay, if we want to know this side here, this height with this triangle, we have the opposite over hypotenuse, which is so, right? So then we have that our height here is going to be d, or our distance here, times sine of 5 degrees. Okay? All right. Let's quickly look at what this sine theta is, or this theta prime here is. Okay, since it's not the same as here. Okay, so when we're looking at this situation, we have a force, oops, a force, hold on. Okay, so we are looking at our frictional force, which is going to be opposite to the way he's moving, right? Because his force is going in that direction. So our frictional force is trying to pull him back. That's how I think of it. And our distance is going to be in the exact opposite direction, actually. Our displacement, I mean. Okay. So with that information, our theta prime should equal 180 degrees, meaning our cosine of theta prime is equal to -1. Okay. So again, our frictional force is going to be in the exact opposite direction of this displacement. Okay. All right. So now we can write this equation again and say 1/2 mv0 squared minus, because of this here, F times D, which is the distance traveled, equals mg d sine 5 degrees. Okay, so all we need to do is solve for our distance d, okay, and then that will answer our problem of how far he slides. Okay, so let's go ahead and do that. let's say 1/2 mv naught squared equals, we're going to have a f plus mg sine 5 degrees, and all of that times d. So hopefully you see what I did. I moved this guy over, right? I put plus fd on this side, and then pulled out my d to the right, okay? All right, so then I can rearrange this one more time by dividing by this factor, since we know all of these values, okay? And it will be 1/2 mv naught squared divided by f plus mg sine 5 degrees. Okay? So, oops. We can go ahead and plug all of our values in. Our mass was 65 kilograms. Our velocity, our initial velocity, was 6 meters per second. Our force, or our frictional force, is 450 newtons. Again, our mass is 65 kilograms. Our G is 9.8 meters per second squared, and times sine of 5 degrees. Okay, after plugging all of that into your calculator, you should get 2.31 meters. Okay. And again, you can check your units. You will get, from this, you would have gotten Newton meter over Newton. Again, you'll end up with your meters here. Okay, so that is my distance traveled. All right, so go ahead and take a break. I will come back talking to you about a tiny bit more, and then that should be good for this module.